The topic today is space weather. In this lecture, we will define and understand the basics of what space weather is, and we'll also try to find out how the space weather is related to GNSS. So wherever you will find GNSS and its applications, you will see that the space weather comes into picture in a certain way. So the title of this lecture is Introduction to Space Weather. So to begin with, let us understand what is meant by space weather, the basic definition. Now we all know what weather is. So whenever we say weather, we talk about the local weather which we find on the surface of the earth, the tropospheric weather. So this weather is a short-term local phenomena. So these two terms are very much important. One is short-term, another is local. Short-term means at your location, the weather in the morning may be sunny, whereas when it comes to afternoon, it may become cloudy. So the weather is changing over short terms of time. And similarly, the weather in a place in India, say Kolkata, is very much different at the same time to the weather in London. So this is location dependent. So these two terms, if we understand these two terms, it would be very easy for us to appreciate the definition of space weather. So space weather defined as the term that describes the condition of the space environment near Earth. Just note this term near Earth. I'll explain why we have put this, which is determined by the solar activities and the associated related field emissions. So it is a short-term condition. So notice two terms here. One is near Earth. So this mentions that the space weather which we are seeing from the Earth may be different from the space weather at Jupiter. This Jupiter also experiences certain space weather, but that is different from the space weather that we are experiencing at the Earth. So this is location dependent, but in a different scale. At the same time, you see in the definition that it is determined by the solar activities and associated radiated fields and emissions. And these fields and emissions are different and short-term in nature. So the space weather which we experience over the Earth is also short-term in nature. So overall, if we combine these two, so space weather becomes a short-term condition of the space environment near the Earth, and which is determined by the solar activities and associated field and emissions. Now, where from these fields and emissions are coming? It's coming from the sun. So the interplanetary space, the space which is there between the sun and the Earth. When we were in our school or when in our childhood, we used to think that the space between the Earth and the sun is vacuum only. And from the sun, it is only the sun rays, the solar energy, the solar heat is coming. The sun rays are coming only. But it is not so. From the sun, there are so many things coming, and which we'll find out here. The things which are coming from the sun are the charged particles. There are different types of charged particles which are radiated and emitted by the sun, and which are received at the Earth at different levels. And also there are magnetic fields. You know, there is a magnetic activity occurring continuously in the sun, and the magnetic fields which are generated at the sun, they are radiated out and emitted out, and they reach the Earth and the interplanetary space. They even go beyond the Earth and at the end of the solar system, and also beyond that. We'll learn about this. So the magnetic fields, the electric charges, these are the things in addition that comes from the sun to the earth. And while reaching the earth, they create their impacts. Where do they impact? They impact at the geomagnetic field, the magnetosphere, and also inside, they get inside that, and they sometimes reach the lower atmosphere and creates different events. To learn about space weather, we need to monitor that, measure the parameters, and this is done by different space agencies using satellites. So sending satellites in deep space and near Earth satellites, and also using ground-based instruments. So getting a little bit into the history of space weather. History of space weather itself is a fascinating topic. The first drawings of the sun with the sunspot were made by Galileo Galilei. And he observed that there are certain black patches on the surface of the sun. And it was termed as the sunspots. And those sunspots were always had been some topic of curiosity for the human beings, particularly the scientists, that why these sunspots occur. Now in 1859, Richard Hodgson independently observed the huge explosions in the sun, and it was named as solar flare. And very near to it, means over time, that within a day or two, it was observed that the geomagnetic storms occurred on the surface of the earth. So it happened not only once, but more than one time. So it was suggested that there must be some connection between these two, that whenever there is a flare or something like that is happening in the sun, some geomagnetic activities is happening on the earth. So is there any connection between these two? Also, there was an observation of the comets. The comets, as you know, it has its tails, and these tails are formed of two kinds of particles. One are charged particles, and one component of it are the neutral particles. And it was observed that whenever a comet passes in front of the sun, the tails divides into two. It was wondered that why such things happen. And it was suggested that there must be certain charged particles which are emanated by the sun, and which deflects the charged particles which are there in the tail of the passing comet. And also there was auroras which were observed. Now, after that, in 1958, Parker put forward his theory of supersonic solar wind. And it was probably Luna 5 or Luna 3 through which the charged particles in the interplanetary space was particularly observed. If we bring out that, what are the drivers which are responsible for the space weather? So what governs the space weather? So definitely we have come to know by now that the sun is the ultimate driver of the space weather, because it is the activity of the sun that governs what the space weather would be at the Earth, at the Jupiter, or at Neptune, or anywhere over the solar system. So in addition to the charged particles and the magnetic fields, there are emissions in different bands that many of our earlier lecturers have spent time on that emissions are there in different bands: X-rays, soft X-rays, EUV, UV, optical, and infrared. And so there are over a large band of spectrum, the emission of the sun is there. So, and some of the radiations, they do define the space weather. So, one thing to mention here that the radiations from the sun, the electromagnetic radiations from the sun, they vary over time. The amount of particles which are being emitted from the sun, what it is today, it will be different tomorrow. So these are continuous in nature and they are emitted from the sun. Now from the sun, also there are magnetic fields which I have mentioned. So the magnetic fields fills up this interplanetary space. And there we call it as interplanetary magnetic field or IMF. So what are the interplanetary magnetic fields? What are their strengths? How they are measured? We'll describe a little bit of it in subsequent slides. Now they all modify and define the space weather. In the pictures here, you can see the sun being photographed in a definite spectrum of, in a definite bandwidth. Now in the second one, in this one, you see the sun in different phases of activities. So there are lower activity period and higher activity period. So the activities forms a cycle, they follow a cycle called the solar activity cycle, which will come in detail. And there are certain events which are happening on the sun. There are solar flares, there are CMEs, the coronal mass ejections, the solar flares, and there are also certain phenomena happening here in addition to what we have mentioned. Now the solar activities, as we were mentioning, solar activity, at how much magnetically active it is, it follows a definite cycle, and that cycle is actually of 22 years. Now in these 22 years, what is happening? Now you know the sun has its own magnetic field, but like our earth has its own magnetic field, so something there inside the earth which is generating a magnetic field around it. So the earth is like a big, huge magnet. The sun is also like that. It is also generating a magnetic field. The sun's magnetic field are somewhat different from that of the earth. The earth's magnetic field is almost constant. You can broadly take it as constant. It's changing, but the change is secular. It's changing very slow. But the sun's activity and its magnetic activity is a little bit faster. It's not secular. It changes over a period of 22 years. So the poles of the magnet, if we talk in a very simplistic manner, the poles of the magnet which the sun's activity generate, they flip, they move, they constantly change the direction, and they come back to the same position after 22 years. So for example, if today I have a north pole at the top of the sun and south pole at the bottom of the sun, then slowly these poles will rotate themselves, and gradually after 22 years it will again come back to the same condition, the north pole at the top and the south pole at the bottom. So after half the time period, so in 11 years, what will happen? The north pole of the sun, which was at the top, will go at the bottom, and the south pole of the sun, which was initially at the bottom, will come at the top. So this is a 11-year cycle. So generally we talk in terms of the 11-year cycle. In an 11 years period, the sun's activity shows a trough, going up, the activity rising, going to the crest, that means the activity coming to the maximum, again coming down, the activity reducing, going to the trough, the activity coming to a minimum. So this is one period of 11 years, which is called one solar cycle. Now, Currently, we are going through the solar cycle 25. It started in late 2019 and we are in the fourth year of the solar cycle 19. So you must be understanding that if we are almost at the middle of the 11-year solar cycle, because if we take roughly as a 11 years cycle, it's an approximation. It's not always 11 years. It may go to 12. It may come down to 10.5 or so. But on an average, it is 11 years cycle. So we are at the end of the fourth year of the cycle. So we are almost reaching the crest of the activity. So over these years, we have seen a rise in the solar activity. So as the solar activity increases, so initially when the solar activity was at its trough, at its minimum, there are minimum number of sunspots. And as the solar activity increases, the number of sunspots also increase. And at the crest of the solar activity, we get a maximum number of sunspots. So let me give you an idea of what can be the number of sunspots. So at the trough, when the activity is minimum, for a number of days, say 15 days, 20 days, we may see a spotless sun. There is no spot at all. Whereas when it goes to the crest of the solar activity, we may see maybe around 80, 90 or even crossing 100 numbers of spots appear on the sun, and there won't be any spotless day during the solar activity. Now, why does the solar sunspot appear? It's a different topic, but very briefly and very simplistically, let me tell you that there are solar magnetic lines of force. Suppose it is originating from the north of the sun, the north pole of the sun at the top, and it is reaching the south pole of the sun at the bottom. But the poles are not at the surface. It is somewhere inside that. And some of the magnetic field lines run inside the surface of the sun itself. But due to the pressure gradient and due to the buoyancy, these fields sometimes come out through the surface of the sun. So there is a perpendicular magnetic field which is coming out from the surface of the sun. Now, whenever there is a magnetic field coming from the surface of the sun, the charged particles, the plasma, the sun, they cannot come in those big numbers, the vicinity of those places. So, vicinity of that area from where the lines of forces are coming out, they become relatively cooler. The temperature of those places come relatively less compared to its adjacent areas. And that's why they appear dark or relatively darker compared to the adjacent area of the sun. And that's why they appear like a spot. So they are called as the sunspots. So more the activity of the sun, more is the probability that the magnetic field lines, they come out, and that's why the number of sunspots increases. At the same time, you will appreciate that if it is coming out, but your south pole is somewhere inside the sun itself, so somewhere it must get inside the surface of the sun again. If at some point it has come out, at some point it has to go within. So if there is one sunspot of such certain polarity of the magnetic field, there should be another sunspot with a just opposite polarity. So sunspot appear in pairs and with opposite polarity. Okay. So this is in brief about the sunspots. And also when the activity is less, it will see the sunspot appearing at one phase of the sun near the poles, whereas as the activity increases, it will move towards the equator. Okay. Now this chart shows how the different solar periods, they have shown the sunspot numbers with time. So this is the 25th solar cycle. That means 25 into 11 years back, the solar cycle counting was started. So it does not mean that 25 into 11 years back, the solar cycle started. It means the counting of the solar activity period started from that period. Okay. So this is the 25th one. So we are somewhere here in this chart. Okay. One thing you must have noticed, that the peak of the solar activity crest right from the cycle 21, it's gradually reducing down. Say this was 24, 23, 22, and this was 21. It is gradually reducing down. So when we were in the solar cycle 24, it was apprehended that whether we are moving towards another Maunder minimum. That means when there will be no activity with a crest, so sun will go to a long slumber. So sun's activity will stop for a long time, whether we are moving towards that or not. But in solar cycle 25, we are seeing that it's again towards a rise. The solar crest is proposed or predicted that solar cycle 25 crest would be much higher than the previous one. So now the solar radiation storms. So what is solar storm? So we know what a storm is. We come across the storm in our daily life. Over a year we can see, we say, so many storms happening. But those storms are the tropospheric storms, which are happening over the surface of the earth. But there are radiation storms in the earth. So how do we define our conventional storms? Whenever the winds are flowing at a rate which is not nominal, which is much higher than the nominal, we call it as a storm. Similarly, if we draw an analogy between these two, similarly, the sun is it's emitting the radiations, it's emitting the particles at a certain nominal rate every time. But whenever this radiation rate exceeds a certain amount, then it becomes a storm. Okay. So very simplistically, this is what a solar storm means. There are different levels of storm. There are radio bursts which are measured in SFU, the solar flux units. There are X-rays, as I have mentioned. There is a wave. As it emits in radio waves, it also emits in X-rays. So X-rays are measured in watts per meter. There are class A, class B, class C, class M, and class X. Class X is the highest amount. It is 10 to the power minus 4 watts per meter square. Then if it is say 5 into 10 to the power minus 4, we call it X5 or 5.0x. So there are also particle emissions. The unit is not there. It is PFU. PFU is the particle flux unit. Okay. So whenever the numbers of these units goes high compared to the nominal values, then it becomes a storm. So the solar flare, we have come across the term solar flare many a times. And the solar flare is a sudden flashes of brightness on the sun's surface. There is a huge amount of energy which is released, and along with the electromagnetic radiation. And it affects the Earth's ionosphere and cause radio blackouts or interferences. As I mentioned, the radio emissions is there. So if there is an abrupt increase in the radio emission, it affects the Earth. If there is an abrupt increase in X-ray emission, it also affects the Earth, its ionosphere in a different way. So, but why these flares occur? As I mentioned, there are magnetic fields inside the sun. So sometimes it happens that these magnetic fields are not in a regular fashion. So there are sometimes loops which are formed of these magnetic fields. And the loops, sometimes they reconnect. Reconnection of the magnetic field is a very important topic for the space weather. So the reconnection of the magnetic fields happen. Now, whenever the magnetic field is reconnected, it's like you stretch a rubber band and you suddenly release it. Okay. So whenever you are stretching a rubber band, and then all the energy is stored within the band itself. Okay. But when you release it, the release occurs when there is a reconnection. Okay. And a part of the magnetic fields goes away while the rest part gets relaxed. So whenever you release the rubber band, what happens? The rubber band gets relaxed. It starts oscillating, it starts vibrating. The energy which was there as in form of a potential energy, it shows up in form of kinetic energy. So a large amount of energy which is there in form of the magnetic energy, they got released and they come out in form of kinetic energy. And whenever there is an increase in kinetic energy, they are passed on to the plasmas. These plasmas, they radiate, and their X-rays and radio burst and all these things occur. So we won't go into details of that, but this is the reason why these solar flares are happening. Now there is also something called a coronal mass ejection. So these are very common terms we are coming to hear in current days. So the coronal mass ejection is, from the term itself, you can understand that there will be a certain amount of mass which are ejected the sun along with energy. So you can see in this corona graph, this is called the corona graph. This disk blocks the main disk of the sun. This circular aperture closes the disk of the sun, main disk of the sun, so that we can see the corona which surrounds it. And we can see here a large flash coming out from the sun itself and getting detached from the sun and going out into the interplanet. So this is also a result of the reconnection which is happening there. And this flash is nothing but a lump of plasma which is getting detached from the sun. So why it is getting detached from the sun? There is always plasma which is there associated with the magnetic fields. Now, when the magnetic fields get reconnected, the part that detaches from the main field, they travel out and carry billions of tons of materials. So on reaching the Earth, they can cause geomagnetic storm, they auroras, sometimes damage to power grids also, as I have mentioned. Now coming to the solar wind. Solar wind, as I have mentioned, is perennial. Perennial means it is running, it's happening all the time. So it is there all the time. Now solar wind is composed of charged particles which are coming out from the solar corona. Now why they are coming out? These particles have energies. These charged particles, the plasma which we call, carries large amount of energy. But they are bound to the sun due to the gravitational pull of it. Now there is a pressure gradient because the interplanetary space is vacuum. So the pressure gradient is there. So out of all these three, if there is a disbalance, then the particles come out of the sun and they travel through the interplanetary space. So every moment solar particles are coming out from the sun, and this is called the solar wind. Now when it reaches, now it travels through the interplanetary space, and these solar winds, I can say that these are very important. So had there been no solar wind, the solar system wouldn't be existing here, because these solar winds define the heliosphere. So they form a bubble around the solar system so that the outer galactic particles or the galactic particles from outside the solar system, they don't get inside this bubble and cause any problem to us. Okay. So these solar winds are the soldiers that the sun puts at the boundary to keep to keep our solar system safe from any external invasion. So they move through the interplanetary space with supersonic speed, carries magnetic field along with. So when these charged particles move, they carry with them the sun's magnetic field with them, which we call as the interplanetary magnetic field. And these are carried till the end of the heliosphere. And it interacts with the planets and defines the boundary of the solar influence. So the kingdom of the sun is kept secured by the solar wind. Now let me tell you that at the edge of the Earth, that means where the magnetopause is there. So what is the solar wind velocity, solar wind particle density? So these are the parameters through which the solar wind is defined. So at that location, typically the solar wind velocity is around 300 to 600 kilometers per second and becomes like 600, 700 kilometers per second. This is the velocity with which the charged particles travel through the interplanetary space at the location of the Earth. So if it is around 300, 350 kilometers per second, we call it as a slow wind. But if it exceeds 500 kilometers per second, we call it as a fast wind. So there are slow solar winds and fast solar winds. Now, the solar winds, the fast and the slow solar winds have their origin in the sun itself, and there are different locations from which the solar winds originate. The fast solar winds generally originate from the coronal holes, whereas the slower solar winds, they come out where there is a dense coronal plasma over the period of 11 years. Now, when the activity is low, then the coronal holes are prevalent. Most of the places we only near the equator of the sun, we see very dense plasma of the corona. Okay. Activity, the dense part of the corona, they extend towards the pole. So the coronal holes, they get reduced. And during the peak time of the solar activity, most of the sun is covered with dense corona and the number of coronal holes is less. So the faster winds are more prevalent during lower activity period, and the slower winds are more prevalent during the higher activity period. Okay.